Welcome back to the computational finite difference method. I'm Sabir Ahmed again. In this lecture, I'm going to show you how to solve the 2D example. And in this lecture, I'm going to solve a 2D differential equation using the Laplace transformation, or Laplace equation, and how we can write this and how we can write two-dimensional code in MATLAB. Because in the previous lecture, I've already shown you and I've taught you, how to write a code in for one-dimensional case. And in this lecture, I'm going to show you in two-dimensional case. Okay, let's get started. Laplace equation. So from the Laplace equation, now we do know about what is Laplace equation. Anything can on a many differential equation can be solved by the Laplace equation. For example, say at first, say I think we have to determine our domain at first. So for example, we have our domain here. For example, it's a two-dimensional domain, right? Okay, yeah, it's a two-dimensional domain. So is x-axis. Say for us this is the length, right? And this side represent the alien g, this represent length, and this side and the width. Okay, so for example this is 0 to L, and this is 0 to W, right? So we have to, so we have fixed our physical properties, physical domain. So we have a domain whose length is 0 to L and who has width 0 to W, and we have to discretize this domain, right? So for example, you want to discretize this domain like this way. This and that, yeah. So for example, I'm going to discretize this. I'm sorry because my handwriting is not good. Yeah. So for example, this is our domain, right? And we have so we have 1, 2, 3, 4, 5. Yeah, in this 5. Yeah. So we have to solve our general equation, general finite difference approximation, and finite approximation in each node, right? So we have, say for example, in x-axis we have n x equal to 5 and n y equal to 6, for example. So in x we have five nodes. We have divided in x-axis, along the x-axis we have divided the our domain into five elements, and in y-axis we have divided this domain into 6 segments. Okay, so we have total 5 into 6 equal to 30 nodes. 30 nodes or something like that, right? Okay, fine. So in 30 nodes we have to calculate our general finite difference approximation to 30 nodes. That means we have 30 unknowns, so we require 30 general equations. So we have to solve this. Okay, let's go. This is a physical domain, and we have to, these are the boundary condition, right? These are boundary values, and these boundary values should be fixed or should be determined before I go to this. So we have to calculate only this. These are the unknown values. These values are unknown, so we have to, okay, let's change the color so that it will be better for us. um, say we have a domain to have to calculate this and this, and all other things, all the other things are boundaries, so we have to determine only this, but the boundary conditions are given. We're given the boundary condition here, all these things, yeah. Something like that. So yeah, I'm going to go this. Okay, let's go to the equation, our general equation. Then you have to solve. This is the top boundary condition. This is the top. This is the top boundary condition. This is the right. This is the right boundary condition. So it is our wish or our approximation how we can determine this is the left, left, and this is the bottom. Okay, so we have to determine our top boundary condition, left boundary condition, because for example, in case of temperature, say in this lecture I'm going to show you how temperature propagate if we given some boundary condition. For example, this is a plate, right? Okay, and if the top value, that means all the temperature here along this line, along this line is, say for example, 100. Say for example, what is the temperature is this, if this the temperature is 0, and if this is temperature is 0 along these bottom boundaries, and if this temperature, say for example, say 10, okay, 10 degrees Celsius. Then how this 100 and 0 or 10 degrees Celsius will propagate through this, and how will this? So we can solve this by using the Laplace equation. So you have to determine our the top boundary condition, left boundary, right boundary condition, left boundary condition, at the same time bottom boundary condition, right? So we will be given this. Okay, so this is the boundary condition. So how we can solve this? Let's go to the equation. So we know the Laplace equation. Say for example, our temperature is phi. Okay, so according to say d square phi dx square plus d square phi dy square is equal to 0, right? So this is a Laplace equation for the case we are considering in this lecture right now. Okay, so we have to replace this differential term and this differential term by the finite difference approximation. So what is the finite difference approximation in this case? We have two different finite difference cases at this, because we have to consider the two things here along the x-axis and the same time along the y-axis, right? So for example, here we have to determine, we want to find the solution at this point. So now we have to consider along this axis as well, at the same time along this axis as well. So let's go to this. Okay, so we assume that the distance between the grid nodes along this axis and along y-axis is same. That means if this is ace, the distance between the two successive grids along x-axis is ace, then we also assume that for a simplicity, later we can make fix it. It's the same. So this is equal to ace and this is equal to ace, same. Okay, yeah, for assumption. So let's replace this. So we know for this portion we know. So how we can solve this? Yeah, yeah. So we can replace. We are replacing these values. How can replace this? Say for example, phi I plus 1 comma j minus 2 phi I j plus phi I minus 1 comma j divided by s square plus phi I comma j plus 1 minus 2 phi I j plus phi I comma j minus 1 divided by s square equal to 0. Okay, so why I have written here I plus 1 and why not here? Because we are this differential term is with respect to x, so we are considering x. I means we consider I is varying with x along the x-axis and j along the y-axis. So this should be varied along the x-axis, right? Okay, I plus 1 comma j, 2ij and I minus 1, and as it is the is the differential term with respect to y, so we have to consider the y j plus 1, that means j along this axis, y axis j plus 1 ij and j minus 1 and something like that. So if we write this equation, so we have this h square and this h square is the same, so we can bring this out and multiply with 0, so it should be 0. Yeah, so we have the final equation, something like that. So we have here, so phi here is the phi, oh, problem here, I plus 1 comma j, sorry, I'm getting some problem here. I'm erasing. Let's choose our and color should be, I think in color should be red. It'd be better for us visualize. Yeah. So you can write down, we have 2ij has two terms, so it should be the minus 4j, something like that. Yeah, so it should be here phi I plus 1j comma minus, sorry, plus phi I minus 1 comma j minus 4 phi ij plus phi I comma j plus 1 plus phi I comma j minus 1 equal to 0. Okay, so we are interested to find out our solution at this point, phi ij, right? So we need the four neighboring points. So for example here, so I'm going to draw another, sorry, I have to erase this. Yep. So for example, I'm going to draw the figure here. So this, this, and that, yeah. So if it is ij, if it is I comma j, and this point should be the I plus 1 comma j, and this point should be the I minus 1 comma j, and this point should be the I comma j plus 1, and this should be yeah, I j plus I'm sorry, I think I have made mistake. Yeah. Yeah, I'm sorry, I have to remove this. So I'm going to go, okay. Yep. So if you are interested to find out here I comma j, then this is the row, and the one row, and this is another row, and this is another row. Okay. So if this is the row, for example, this is the I, this is another column, so I j plus 1, and this should be the I j minus 1, right? And this should be the I plus 1 comma j, and this should be the I minus 1 comma j, right? So we need only the four neighboring points only. So I plus phi I plus 1j, phi I minus 1j, phi ij minus phi ij, and something like that. Now, all the coefficient in this general equation are 1, so we don't have to worry all about that right now. Because we have coefficient here 1, we have coefficient here 1, we have coefficient here 1, and we have coefficient here 1, something like that. So if all the coefficients are 1 except this minus 4 coefficients, so we have to so this is our general equation. Change the color. Yeah. So this is a generalization, and we have to transform. We have to solve this generalization to every node, and it totally depends upon us how many nodes we are interested to solve this. Okay, so we have to solve. If we have 100 nodes, then we will get 100 unknowns, 100 unknown values. Then we will also I get 100 equations to solve or to find those 100 unknown values. Okay, yeah. So this is a general equation. You have to solve this, and now we have to transform the system of 100 equations. Then from this 100 of equation, you have to transform this into matrix form so that we can solve easily. Okay, how we can do that? Okay, we can do that in very similar way we have done in previous lecture in one day example. This same we have uh, something like that. So before going through this, I'm going to make you understand we have some complication here in 2D. That's why I'm going to show a little bit something in MATLAB extra so that you can understand how we can go through this in simply. Okay, let's go to the MATLAB then. So we need only the four neighboring points, right? So if we know the ij, say for example here if we know the ij value, then we need only I plus 1 comma j, I minus 1 comma j, I comma j plus 1, and I comma j minus 1. So we need only this four terms should be needed to solve this equation for every node. Okay, so how can we know the coefficient of every time is 1 1 and 1, and only the that particular value at that node would be the minus 4, something like that, right? Okay, so let's go to the MATLAB and to start with. Now I think we should keep. Yep, let's go to the MATLAB. So I think it'll be better. So I've written some code for you in previous so that clear all the things should be cleared, and CSS something like that. Yeah, okay. For here we also we have to determine the physical property determination. We have some physical property. So for example, we have a domain having 10 meter or 10 centimeter or 10 unit length. At the same time, we have 10 unit width. yeah, numerical property. So we want to determine our domain to be divided along x-axis into 10 segments and along y-axis into 10 segments, same thing. Yeah, so lvx, what are the points here? So we want to determine our 0 to lx, that means up to 10 into nx segments, right? At the same time, lx is linear space. So you know already what is linear space function. Linear space function is a function that divides segments into equal parts. Okay, so we'll get the vector lvx and lvy, and we know the dx and dy because if we take lvx nx minus lvx nx minus 1, so we can find out the difference between two successive nodes along x-axis. At the same way, you can find out the difference between two successive nodes along y-axis, dy. Now it's time to matrix initialization. So we have a matrix, it's a force vector or load vector, something like that. So RS is zeros, nx, y, because we will have 10. We have divided our grid, we have divided our domain nx, that means 10, and in y ny equal to 10, that means we have unknown grids. Number of unknown grids is 100, so we must have 100 grids, so 100 columns, and this is the column matrix, a column vector, and one column, something like that. And zeros, stiffness matrix, so it is very important. So in stiffness matrix we will have 100 columns and each 100 rows, and each row represent one equation at particular node, right? Okay, so we have 100 nodes and 100 columns. So this should be the square matrix, and you know why I have written 100 nodes and 100 rows and 100 columns. So you have already learned in the previous lecture. Okay. Okay. So, but I have already said you that we have some complicacy here in two-dimensional problem solving in MATLAB or something like that, or in coding. So we have to do something little extra for convenience, for a simplicity. Okay, let's go to the MATLAB in previous section so that I can understand. Okay. Uh, so let's we divided our x-axis along 5 nodes. Yeah, we'll have 5 nodes, and y will be along y we divided our domain into 6 nodes. Yeah. So for example, we are determine domain, our stiffness matrix, let's say A, and initially it should be 0 because then we'll put our values in a specific position. Okay, so zeros, x5, so this should be the x and y, right? Okay, so this is our stiffness matrix. Sorry, this is a domain. This is not stiffness matrix, this is a domain. Okay, so what we are interested to do, these are nodes, right? So this is the 1 1, this is the 1 2 1 3 1 5 or something like that. So instead of doing 1 1 1 2 1 5, say it is a 5 6, right? So we are interested to numbering the nodes. For example, this should be the 1 2 3 4 5 6 7 8 9 10 and so on, and up to 30. And this is the 30 number nodes, right? Because we have 5 into 6, 5 into 6 would result as 30, so this should be the 30 number nodes. So we will do that in 30 number nodes. Then we will extract which nodes are boundary values. These are the boundary values, right? I'm going to write something so you can understand. uh, these are the boundary values, and these nodes are also boundary values. These nodes are also boundary values. These are boundary nodes. So for example, and if I draw or something like that here, along x-axis we have divided our into 5 segments. So 1 2 3 4 and 5. Yeah, 0 1 2 3 4 5. Yeah. So, and a y-axis it should be the 6 1 2 3 1 2 3 4 5 and 6. Say something like that. These are domain, right? And what is the boundary values here? So these points are boundary values. These points are boundary values. These are the boundaries. So we have to fix this boundary condition here. right sir? Okay, and we have only these values are unknown values to be determined because these are given to us. So so we have determined our matrix. So each node, so this node is represented by this value, and this node is represented by this value, this node is represented by this value. So for example, it is 30, and 30 number nodes represented by this value. Okay, I hope you have understood all about that. And this is the solution. This is the way how you can transfer a physical domain into code, MATLAB code, something like that. So we have to determine, say, what we are here, because we are numbering the nodes. This should be the 1 2 3 4 5 6 7 8 9 10 11 12 and up to 30. Okay, so this should be the 30. Okay, so why we do that? Because I've already said that if you don't do that, and we'll face mass complicacy. That's why we are interested to do that. Right. Okay. So how we can do that? It's very easy. And so for example, we can write down, or say for example for, and we can write down code for I equal to 1 up to x, for j equal to 1 up to y. Then every node, say for example say a I command would be 1, say for example 1, yeah, let's say I don't know, it should be the 1. Okay, now this should be the number n. I think I made a mistake. Okay, let's first define something. Let's first define something. Wow, we can. Okay, CLC and END something like that. Yeah. So a equal to zeros, say 5 6, and we have something like that. So for example, n equal to 1, for I equal to 1 up to x, for j equal to 1 up to y. Then the cell value a sorry ij would be n. Okay, so ij would be n, and then n equal to n plus 1. Okay, so and I hope it will be working. Yeah, so right now let's say what is a, yeah, so we have got this. So this simple formula can make us understand. So 1 2 3 4 5 6 7 8 9 10, so we will have 30 equations, right? So one equation represents a 30 columns, right? So in say for example, we are interested to determine the 10th number equation. That means at number grid 10. So at point 10, at that particular row, so we know, say for example here. So I'm going to make you understand all about that. So that, yeah. Say we will have 0 0 0 0 0 0 0 0 0 and up to 0. This is 30, right? So same way 0 0 0 0 0 0 0 0 and up to 30, and this way we will have 30 equations, 0 0 0 0 0 0 and up to 30, something like that. Yeah, so we have a matrix something like that. This is the stiffness matrix, and we have to determine say for example we are interested at number 10. Say for example we are interested at number 2 or something like that. At number 10, say 0 0 0 0 0 0 0 and up to 0. So for example, this is the 10 number equation. We're interested to find out the 10. So for example, this is the 10 nodal points. So 1 2 each column. So this should be this is the coefficient value of 1, and this is the coefficient value of 2 nodes. This is the coefficient value after, but we know from the general equation we know only the 4 nodes to calculate, right? So we do not have, we will have all the other node values should be 0 here. So all the other node values should be 0. So for example, these are 10 nodes, okay? These are 10. So this should be the coefficient value, this should be the -4, because from the equation we know all about that. And we have to find out the other 4 columns, in which columns we have to put the 1, right? So we'll see later. Okay, so these are the boundary condition here. So what are the boundary values here? So we have boundary values of 1 to 6, 1 2 3 4 5 6, um, then 7, then 12, then 13, then 18, then 19, then 24, then 25, 26, 27, 28, 29, and 30. So all the node values, these are the boundary values, boundary nodal numbers, right? Okay, so these along in these node values, some predetermined or some something to be fixed before we go through our programming, right? Okay, so we'll see this later. Okay, fantastic. Let's go to our MATLAB code. So different to the numbering. So how many nodes we have here? Here 1 to 6 and 1 to 6. So we have number of how many boundary nodes we have here. Say for example, we have here this. So how many? This should be the 6, right? And this should be the 6. This should be the 6. Okay, so in along axis we have 6 times 2 plus we have these boundary values, but we have common. So 1 2 3 here, 1 2 3. So 3 times 2 equal to 12 plus 6 equal to 18. So we have 18 boundary values and boundary nodes. Okay, so we can write down in general formula here. How you can write down the general formula? Nx times 2 plus ny minus 2, because y minus 2, because we have to subtract the two values from the ny, times 2. So this is the second coordinate. So these are the number of boundary nodes here. Okay, so these are the boundary nodes. Okay, so let's go to MATLAB right now. Okay, so we know this is the boundary nodes, nx minus 2 plus ny minus 2 into 2. This is the number of numbering the nodes. When this segment is dedicated for numbering nodes. Okay, so equal to nx times 2 plus ny minus 2. So this is the total number of boundary nodes we have. So we are going to make a matrix, column matrix, one row, or sorry, row matrix. So this matrix will represent the numbers. Okay, so which number this matrix? Okay, say number 1 b1 cell. So cell is nx minus 1, our domain. So cell is our domain, because a0 is nx into ny. We have seen here cell equal to a equal to cell. So nx number x equal to, along the x-axis we are interested to divide, and y. So in this case our cell, so cell is 0 cell minus 1. So you have to determine all the cells. So we divided these two things. Cell I is equal to numbering plus 1, you know all about that, and boundary values. If the I equal to 1, or this means represents or j equal to 1, that means if I equal to 1, this all the row, if the row is 1, that means here if the row is 1, all the columns in row 1 are boundary values, and all the columns in row nx, that means in I equal to nx are boundary values, and all the j here are the boundary values. All the same column in different rows are the boundary values, right? So I have written code here. if I equal to 1 or j equal to 1 or I equal to nx or j equal to nx, these are the boundary nodes, and this matrix will be filled up by the numbers. Okay, so we can get this. Else, if this doesn't happen, then this will happen, right? So we have determined our bounded node. So let's see in debugging mode or something like that. So for example here, so we have 36 boundary values here, 36 boundary values, something like that. Yeah, and we have boundaries 1 and 36, so this should be 36, and this should be filled by this and which numbers or something like that. So this is a filling. It's a 1 2, approximately 1 2, and these boundary values are 1 to something like that. Yeah, so this will be filled. So let's go up to this point and let's go. Yeah, so let's see, all these are the b nodes or matrix which represent all the boundary nodes. So we have boundary nodes 1 2 3 4 5 6 7 8 9 10 11 20 21 30 31 40 41 50 51, something like this. And after this, so we have 30 boundary nodes. We know all about that. And we have cell values 1 to up to 100. So we have got our cell nodes or something like that. Now it's time to determine our coefficient matrix. So you know, our coefficient matrix. In this case we have, oh, I'm sorry, and we've got this. So in this case we have to find out from 2 minus nx minus 1. I have already said in previous lecture, in this lecture as well. So j equal to 2, because we didn't start from 1, because all 1 represents the boundary values, and all at the same in y-axis all the 1 represents boundary values, and nx minus 1, why we didn't replace nx, because nx represents boundary values and the ny represents the boundary values. So kk equal to cell ij. So let's press F11. Let's go there. Say for example something like that. So k equal to 12. So akk minus 12. So we know the diagonal values. Akk should be the minus 4 and all the cell. So kk. So we are interested to replace our values in. Right now we are calculating for a particular node, right? So that node is I equal to 2 and j equal to 2. That means which value, k equal to 12. So 12 number, at 12 number nodes we are calculating. So our number 12 equation, that means 12 number rows in matrix, in coefficient matrix, representing the equation to be solved at 12 number nodes. Okay, so that 12 number nodes, 12 12 is equal to minus 4 and equal to coefficients 12 equal to I, j plus 1 equal to 1. But if we put down this, then we'll get the values. Okay, then we have filled our coefficient matrix, something like that. Yeah, so fill this way, 1 1, something like that. Yeah, so now it's time to apply a boundary condition. How we can do that? So we determined our top boundary value should be 100 degrees Celsius, something like that, and bottom boundary value should be the 20. Right boundary is 30. So how we can find out which are the bottom boundary values and top boundary values? And okay, so from the cell we can find out it easily. It's very, so for example here, top. So cell, all the columns in cell having row 1 is a top, right? Yeah, so what are our top boundary values? These are top boundary values 1 2 3 4 5 6 7 8 9 10. In this case, what are the bottom? Same thing, all the nx row or all the columns in nx row are the bottom. Yeah, 91 92 and something like that, 100. What are the left? This is the left, 1 11 21 31 41 and something like that. Okay, so at the same time we have we can do this, so something like that, 100. So we have very interesting thing here. You see right in right, what is the bottom values of 100 and is the top. At the same time in top we have 10 at the right place, so 10 is twice and 10 is twice. So it's depend upon you, so which one you should be fixed, right? So it totally depends upon you. I keep this as usual and I'm letting this code go on, letting this code goes on, so it doesn't matter. So it's up to you to be fixed by you and according to your research program. So set up the force vector, but set up the force vector and boundary condition. So RISS, we know we have force vector RISS, right? So we have 100 into, we have 100 100 unknown values. So 100 unknown values, so um, we have to replace these top values or something like that. So RISS top, or the top nodes 1 2 up to 10. So RISS, uh, all the nodes or all the something like that up to 10 should be replaced by the top value RISS. All the nodal points of having this top of RISS should be the top value. RISS left value should be left value, something like that. This bottom should be bottom value. RISS right and right value, something like that. So stiffness matrix. So I hope you have got this. Yeah. So say, let's see. Here 100. This is the 100 and 30 something. All the boundary values are applied to the force vector. Okay. The stiffness matrix and boundary condition. Stiffness matrix boundary condition. So it's the same boundary. We know the boundary nodes here. After this, all the boundary values in the stiffness matrix should be the 1. Right? Because you know why it should be the 1, right? In the previous lecture I've already said that. Okay, 1. So yeah, so this the value is 1 1. So we have up to this equation 100. We will have 100 equation, and each equation represents 100 columns or something like that. Yeah, so we can go further. Yes, so I hope I'm gonna get a solution from there. Yeah, I've got a solution. A divided by RISS. So we have determined A is stiffness matrix in the force vector, and then A inverse times RISS. So we'll get our solution to that solution. And how we can represent this? Plot and visualization. So as it is a two-dimensional case, so I have to write some extra code. So we have mesh grid to determine our mesh grid. So we know our x-axis determined, and dx is the difference between two successive nodes along x-axis. So x-axis should be represented from 0 to lx with difference dx. At the same time 0 to dy, and so this mesh grid is a function that will generate a grid according to your given input value. So we have given this input value, and according to this it will find out this. Okay, so reshape, we go there. The reshape are d. So what is d? These are our column vector, so row vectors and something like that. So this should be represented by nx into ny, and the reshape is a function that will transfer these row vectors into nx into ny. That means 10 rows and 10 columns, something like that. This will represent, yeah. So go to the p color, something like that. So it represents this. Our grid values are, we have got our d into row vectors. So reshape is a function that will transfer our domain, transfer into 10 into 10. So it's 10 to 10, and it replaces all the values from this. Okay, yeah. So p color x y r, and xy is the xy. We have got the position xy. We've got the position xy from this, and r is our solution. So from this p color, it will represent the color, something like that. Then we can easily find out our solution. Yeah, so we have got this. So if we put this is our solution here. Basically this is a representational solution, because I put this value should be the 100. Yeah, so his value was 100. Yeah, so let's go to this and say sharing interpret. Yes, so finally you have got this, and a color contour depth. So this is the contour, and this is the color bar. I have this color. So this is the general procedure to write a code. I hope you have understood. If you don't understand, I'm posting this file to the YouTube and something like that, so that you can download it and you can analyze this for your convenience. If you don't get through any point of this, I may write a code wrong way, because I'm doing a lot of things here right now. So please pardon me if you find any error in this code or something like that. Please do not hesitate to let me know about that error or something like that. So I hope you have enjoyed this class. Thank you, and I'm gonna teach you another 2D example in next class. Thank you. Thank you very much, and I'll see you on next class. Thank you.